Welcome to the course module of Communication Engineering. And in this video, we are going to learn about the random process. So far in my previous lectures, I have already discussed about the random variable. And in this lecture, we have to extend the idea of random variable to a time varying functions. So to start with, we have to consider the example of noise, which is available in any electronic circuits. So if we consider the thermal noise, normally this thermal noise happens due to the random movement of electrons and due to thermal agitation. So normally because the number of electrons that flows in a particular circuit, that number of electrons is not constant. Okay, and because of the small fluctuations in the number of electrons, which is crossing unit cross-sectional area in the circuit, there will be a fluctuation in the current. So if we able to measure this fluctuations in the electronic circuit, then we can see that this kind of fluctuations will be quite random in nature. Okay, so there will be a random signal that we are going to observe from any electronic circuit if we are able to measure the thermal noise. So if we consider different circuits, then obviously the noise fluctuations will be random, and obviously we are not going to repeat the similar waveform, but there certain characteristics will be constant. So such characteristics will be your statistical characteristics of the random signal. So those characteristics will be going to be constant. But normally, if you see it's a time domain waveform, that waveform will be quite random, and you can't find any correlation between the two signals, right? N1T and N2T. So normally, this kind of random signals we are going to observe. We can also observe the randomness in our information sources. For example, if I speak something, okay, normally whenever I speak or speaks something, we cannot know what are the content that the speaker is going to speak in advance. And therefore, speech signal is also considered to be a random signal. Okay, so if you record any speech signal, right, that speech signal will have a very random nature. Fine. So these are the your random signals, right? So now we have to think about what is random process and how this random process is different from the random variables. Okay, so if you see the definition of your random process, okay, so normally the random process, if you see the definition, it is a collection of time functions or signals corresponding to various outcomes of a random experiment. So if you remember, when I was discussing about the random variable, I said that in the case of random variable, if we conduct any random experiment, then the outcome of that particular experiment will be assigned by a particular real numbers. So assigning those outcomes as a real numbers is actually called as the random variables. Okay, so here in this case of random process, actually the outcome is not going to be a sample point. Okay, it is not going to be a single real numbers, but that outcome is going to be the time functions. Okay, it will be a waveform. It will be a complete waveform. So and this is the actually difference. In the case of random variable, if you see, we had the sample space, and within the sample space, we had certain number of outcomes. So those outcomes were actually known as the sample points. Okay, it was the sample points. For example, if you take the example of rolling a dice experiment, I had explained you that there are total 6 possible outcomes, 1 to 6. So this 1 to 6 were actually forming the sample space, and each outcome 1, 2, 3, 4, 5, 6 were called as the sample points, right? But normally in the random process, if we talk about the this sample space here, this sample space is normally called as the ensemble. Okay, so it is normally referred as the ensemble, and it will be having the time varying signals. Okay, it will be containing the time varying signals or waveforms, which is known as sample functions rather than sample points. So normally any random variable, In fact, any random variable which is a function of time, it is also called as a random process. So these are the two different definitions. Okay, it is a collection of time functions or signals corresponding to various outcomes of a random experiment, or a random variable which is a function of time is called a random process. So we'll try to understand this, what is random process, by one of the examples. So let us suppose that these are the waveforms corresponding to the measurement of temperature of a certain city. Okay, so it represents that here, if you see this random process actually being represented by capital X T comma zeta I. Okay, so here this particular random process, if you see, this random process is actually denoting you the variation of the temperature of a certain city from a certain time. Let us say it may be from 10 a.m. to 6 p.m. or so on each day. So here this zeta I actually denotes you the day, a particular day. It may be a day one, this is day two, day three, day four, and so on. So normally we can have the large number of such collection of your different waveforms. Okay, so this is the temperature variation over the time, okay, on a particular day. So we can have such a collection of different sample functions. So the collection of the sample functions may be containing a huge number of samples, okay, sample functions. So normally it can be infinite number of samples, or it can be a finite number of sample functions, right? So here we can observe that this is one of the random measurement. Okay, so suppose in a certain day, if we want to observe the variation of the temperature, we have to keep on monitoring the temperature throughout the day. And in that case, such random waveform we are going to observe. Okay, so we don't know at what point of time what will be the temperature exactly, but there will be a certain random variation of the temperature we are going to observe. So similarly, if we go day by day on different days, a similar pattern we are going to obtain, but it will not exactly be the same in the previous case. Okay, a little bit variation in the pattern you may find. Okay, so here all these sample functions or waveforms are actually forming the ensemble. So here we can see if we represent this X is the random variable actually, which is a function of time. Okay, so here we can see this random variables, each sample functions, this collection of all time waveform, this temperature waveform over the time for a city is actually represented by capital X. Okay, and this capital X is actually a function of time t as well as a certain day, a certain day. Okay, so it can be day one, day two, day three. If we are interested in a temperature in a particular month, then we can have this all data for a certain month. Okay, so it may be from the day 1 to day 30. So we can have all this data, right? So here this X is a random variable which is a function of time t, and a particular day zeta I, therefore X t comma zeta I is a random process. So normally this is going to be a random process because it is a time dependent function. This random variable is actually a time dependent function, right? So here this X t comma zeta I is the continuous function of time for a particular day. This is called as a sample function. So these are the each sample functions, right? So these are the called as the each sample functions. So we are having this sample functions, and this collection of all possible sample function is known as the ensemble, right? So normally the number of sample functions in an ensemble can be finite or it can be infinite depending on the random process under consideration. So now we can also take one more example. Okay, so suppose if we have any binary signal generator. Okay, so let us suppose we are able to generate binary signal for about 10 t seconds, right? And the each binary bit is actually represented by a duration of t seconds. So there are total 10 binary bits that this particular random binary signal generator is actually generating. Okay, so as we know, because it is a output of a random binary signal generator, you might be thinking that this signal is actually not looking like a random signal. Okay, so here you can think about that it may be looking like a deterministic signal. Okay, but the thing is that this is again an example of a random process. So why it is a random process? Because if we have a random binary signal generator, and if it is generating 10 bits, okay, over the second of 10 t seconds, right? At that moment, we are going to get there are 2 to the power 10 such possible outcomes. Okay, so there will be a total 2 to the power 10 possible outcomes which is possible. And at what point of time, what will be the pattern of this output of a random binary signal generator is going to be, we cannot ascertain. Okay, so we are not able to tell which particular pattern is going to be occur. And therefore, the output of the signal generator, binary signal generator, is also a random process. It will be a random process, right? So there are total to the power 10 such outcomes. Okay, so this ensemble is actually containing 2 to the power 10 such outcomes, or 10 such sample functions, you can say, because it is a function of your time, right? So this way we are having our random process. So random process could be having a certain analytical expressions also, right? So it seems that because it is a random process, so we may not have the its analytical form, but sometimes we do have a certain random process which is having the analytical expression. So here you can see this particular expression. So suppose if a random process xt is actually denoted by a cos omega t plus theta, then this looks to be a analytical expression because it is having a mathematical form. So we may think that it is not a random process, but if you see, because this theta, this represents you the phase part of your cosine signal, and because this theta can take any value from 0 to 2 pi, so at what particular time this theta will be taking what particular value, we do not. And therefore, if this theta is a random variable which is continuously varying over time, and if it is taking a value from 0 to 2 pi, then there will be such infinite number of possibilities of having the value of theta. And therefore, if we plot this waveform, okay, for the various values of theta, this random process is going to be a random kind of output. So here you can see it is forming this particular waveform, but here you can see in each case this phase part of your random signal is actually changing. Okay, so here this zeta 2 or zeta 1 is actually representing the phase part over here. So if this phase part is different, then we are going to get a little bit different cosine signal, right? So this way we can have infinite number of such possibilities of generating this cosine signal with infinite possibilities of its phase part. Okay, that infinite possibility is actually being varying from 0 to 2 pi, and therefore it is actually referred as the random process. So here one more thing that you have to remember, that in the most of the cases in practical situations, we do not have the analytical expression of the random process. So we actually don't have any analytical expressions, but we are just having the certain observed data. So based on the observed data, we have to take on decision, and we have to take certain measurements, or we have to classify or characterize the your random process. Fine. So here one thing that we have to know is in the most of the cases, analytical expression of the random process is not known, but we can have the ensemble of that particular random process. Okay. So we can just have the ensemble that was obtained experimentally. So we are having the collection of major data, waveforms, or sample functions, and normally we do not have the analytical expressions, right? So suppose if we have such a random process which is not having any analytical expressions, in that case, how to tackle such random process? Okay, so that we have to see. So we have already discussed about the random variables, and I already have talked about the CDF, okay, cumulative distribution function, and probability density function. The same concept can also be extended to the random process. Okay, so here we can define the joint CDF and joint PDF of random process. So here we have to try to understand that suppose that we considering a random process defined by this particular expression xt. Okay, so here I have to you have to understand that let us suppose if we have this time t equals to ti. Okay, so if we consider a certain random instant of time ti, then the outcome of this random process will be denoted by at x t equals to ti, this output will be represented by xi. So here you try to understand here this xi is actually representing you the random variable. Okay, you try to understand it is not representing the actual outcome. Okay, it is the value assumed by this random process at time instant t equals to ti, and that outcome will be called as the random variable xi. So that we have to understand from this graph only. So suppose that this is the previous graph that I had taken to explain the random process that the data is measured, the temperature data that we have measured. Okay, so suppose that in this case at time instant t equals to t1. Okay, so if we do this measurement, you see, to understand the random process concept, okay, we should have the large collection of your sample functions. Okay, so once we have the large collection of the sample function, then only we will be able to tell or characterize the random process. Okay, so here you can see at t equals to t1. Okay, here if we do the measurement, this measurement will be done for all the sample functions. So suppose in this case, if we are having n number of sample functions, suppose that. Okay, so we are having the n number of sample function. In that case, if we do the measurement at t equals to t1, in that case, whatever be the data which is actually we are getting, all this data will come from all the sample functions. So if we are having total small number, small n number of sample function, in that case, the number of outcomes at this point, and which is coming from the different sample function, will be small n. So normally what happens, this outcome at this particular x at t equals to t1 is actually denoted by the random variable x1, and into this random variable x1 we are going to get the total number of outcomes equals to small n. Okay, so and what are those outcomes? That outcome says if we do the measurement, okay, at t equals to t1, we have to tell what is the outcome due to your sample function 1. So there will be a certain amplitude at this point. Then again, we have to talk about at the same time t equals to t1, what will be the outcome due to this sample function 2. Similarly, this is the sample function 3. So what will be the outcome at this point, and what is the outcome at this particular point? So here, this is the random variable x1, which is actually containing the outcomes of this all sample functions at time t equals to t1. Okay, therefore you remember that this is not just the outcome, it is representing the random variable which is containing the outcomes of all the sample functions at time t equals to t1. Similarly, this is the second random variable x2 at t equals to t2. Similarly, at t equals to t3. So if we do this measurement at different instant of time, okay, then we can generate the similar number of different random variables, and that random variable will contain n number of such outcomes, right? So this is the your sample, this is your random variables, right? So here you have to understand this numbers, these are actually your random variables, right? So now we can define the joint nth order joint CDF. Okay, so this is cumulative distribution function. So this cumulative distribution function for this random process xt will be defined like this. Okay, so if it is a nth order joint CDF, in that case this CDF will be written as f capital X, here in the bracket x1 comma x2 up to xn. Then it is at t1, t2 up to tn. So what does it mean to write this particular equation? So this equation means we are actually interested in this particular probability. So what is this probability denotes you? This is the probability that here you can see we are writing capital X in bracket T1. So what does it mean by capital X in bracket X T1? This represents the outcome of this particular random process at T equals to T1, and that outcome is your random variable X1. Okay. So here we have to talk about what is the probability that if we do the measurement at time T equals to T1, then this random variable X1 is actually having its value or outcome which is less than or equals to small x1. Okay. So here this x1 represents you the outcome. Okay. This will be a real number the way we are actually assigning to a particular random variable. So this is representing you the real number, you remember. Okay. But here this will represent you the particular random variable. So here we have to talk about what is the probability this random variable x1 will be less than the particular value x1. Similarly, this will represent you what is the probability the random variable x2. So if we do the measurement at at t equals to t2, what is the probability this value is less than x2. Similarly, this will go up to this particular time. So if we take this random variable xn, then what is the probability this xn is less than or equals to xn, right? So these are the probabilities that we have to talk about in the case of joint CDF, nth order joint CDF for your random process. Okay. So as we know that the CDF and PDF is actually the probability density function is related by we have to differentiate the CDF. Okay. So because it is a nth order joint CDF, so we have to go for the differentiation by n times. So there will be a we have to calculate the nth partial derivative with respect to each random variables, right? So it must be it must be we have to take this derivative with respect to this random variable x1, x2, x3, right? So this way we have to go up to xn. So this way this joint PDF can also be calculated, right? So now we have to try to understand that if we have any nth order joint CDF or joint PDF, let us suppose, okay, in that case we can derive the lower order PDF by this given nth order PDF. So what we can understand is that if we have the nth order PDF, right? From the nth order PDF only, we can derive the lower order PDF. Any lower order PDF can be defined. So here, if we are, for example, you just try to understand this, what is the meaning of this? Okay. So suppose if we have this second order PDF. Here you can see this is defining you the second order PDF. So what is this PDF represents you? This represents you. This is the this PXX is actually x1 comma x2 comma t1 t2, right? So if we integrate this second order PDF, here it is the equation for your nth order PDF that you remember. Okay. So here because we are doing the measurement for n times, okay, for n different times instant we are doing the measurement t1 t2 up to tn. So it was having the nth order PDF, okay, and at that point of time we actually defining this particular probabilities, right? So here you can see here because we have done the measurement only for time instant t1 and t2, so it is representing you the second order PDF, joint PDF. Okay. So if we have this second order joint PDF and if we do this integration from minus infinity to infinity dx2, then from this integration only we will be able to get the first order PDF. Okay. So that will that value will be px x1 comma t1. So it is a similar way. That way we have already if you remember in the case of random variable, I explained you about the marginal density functions, right? So the similar way we can also calculate this lower order PDF from the joint PDF, right? So obviously this is the result that if we have any nth order PDF, okay, if we have the nth order PDF, there is no need to define its lower order PDF, because from the nth order PDF only we can derive all the lower order PDF by just having this particular integration, right? So normally in communication system, if we see in the communication system, second order statistics are very important. Okay, this second order statistics, right? Right. So normally this is very important point. Okay, so second order statistics is very important, right? So suppose if we know this second order statistics, so what does it mean to have this second order statistics? If it is known, what is it, what does it mean? Right. So normally, if we have the second order statistics, it means that at each time instant t, the probability density function of xt is available. Okay. So if this particular function is defined over a certain interval of time, okay, so independent of time, okay, within that particular range, we actually have the probability density function xt. Okay. So at any instant of time, we can have the probability density function, right? This is the meaning of your having the second order statistics. And the second meaning, this is the first thing that is known. And the second thing which is also known is for all choices of T1 or T2, okay, the joint probability density function xt1 comma xt2 is also available. Okay, so this is the meaning if we have the second order statistics, right? So for all choices of T1 or T2 means that, as here you can see, I have taken T1 at this point, and then after a certain time we have considered T2, but this T2 can be anywhere. Okay, so this T1 you can take at this point also. So this can be a T1 here, then again we have the T2 here, or you can take T1 here, then again T2 here. So irrespective of the location of the T1 or T2, if this T1 and T2 is actually within the range of your time over which this sample function is being defined, then we can always have this joint probability density function. Okay, so this joint density function will be available. So this is the meaning if we have the second order statistics, right? So now we have to talk about a little bit, if we have the random process, okay, how to calculate the statistical averages, okay. So as in the case of random variables, we have already seen, we have to calculate the, before that, I will explain one more thing that normally this random process, we can have a continuous random process, or we can have a discrete random process as well. Okay, so how to differentiate between these two? So normally the time instance that we are taking over here, okay, if we take it to be a continuous value, okay, if it is taking a continuous value, or if you define this time variable t, and if you take the samples at any real value of t, okay, if you take any real value of t, and if this sample functions can give you a certain amplitude, okay, and that time it will be known as the continuous random process. But suppose if you take only integer values of t, let us suppose that if it is defined only at the integer points of t, let us say t equals to 1 second, 2 second, 3 second, 4 second, and so on. In that case, normally it will be referred to as the discrete random process. Okay, but in the case of continuous random process, it can take any random, it can take any real numbers. So it can be like 1.25, it can be 1.79, it can be 2.33, and anything else. Okay, so if this time instant t, if it can take any real numbers, in that case it will be known as the continuous random process. Otherwise, if it is a integer value, it will be considered as a discrete random process. So now we can go for the calculation of mean. Okay, and there is another function which is known as the autocorrelation function, which is a very important parameter in the case of random process that we also try to understand. So normally the way we have calculated the mean in the case of random continuous random variable, if you remember, we had this particular expression. Okay, so there we had the random variable x. So we had calculated the mean by following this integration minus infinity to infinity x multiplied with the probability density function. Okay, so a similar expression we can also have for your random process. So here just we have to remember, because this is a this is not a random variable, but it is a time function of your random variable. Your random variable is a time function. Okay, so x, we have to write xt, then we have to average this value. So this will be giving you the mean of this random variable xt. And here this probability density function will also be a function of time. So this is the only difference in the equation, right? So now you try to understand what does it mean by calculating the mean in this case. Okay, if we have the random process, what does it mean to calculate the mean? So here you can consider this problem, and then you will be able to understand what does it mean if we calculating the mean value. Okay, so suppose we have measured the temperature of a certain city in a certain month. Okay, so here this data, let us suppose if it is representing the temperature of a certain city in a certain month. Okay, and it is in between 10 a.m. to 4 p.m. So let us suppose this data is actually being recorded from between 10 a.m. to 4 p.m., right? And then what we are interested in what is the average temperature at 1 p.m. in that particular month. Okay, so because we talk about that we are interested in that particular month, so there must be a 30 number of such sample functions. So this sample function represents you the variation of the temperature in between 10 a.m. to 4 p.m. in a particular day one. Okay, this is representing you for day 2, day 3, and we should have such data up to day 30. So let us suppose in that particular month the number of days are 30. So there should be certain such 30 sample functions, right? Uh, if we wish, we can also have the data based on year basis, right? We can have the data for the last 10 years or 20 years or so that we can increase the number of samples, right? So let us suppose that if we have only the data for the past 1 year, and within that past 1 year, we have done this measurement for 30 days, right? So I can ask you this probability, okay? This particular problem. What is the average temperature at 1 p.m. in that particular month, okay? So we are interested in what is the average temperature at 1 p.m. in that particular month. And I'm also considering that we are actually recording the data at 10 a.m., then 11 a.m., then 12 a.m. So every discrete instant of time, we are actually having this recorded data. Okay, though it is a continuous function of time, you are able to see here. But let us suppose that if we sampling this particular the sample function at discrete instant of time, and let us suppose that we are having data at 10 a.m., then 11 a.m. So every 1 hour we are having the data, okay, of the temperature which is available. So if I ask you that what is the average temperature at 1 p.m. in that month, then obviously how to get this particular average value. Okay, so to get this average value, we have to take the temperature data at 1 p.m. every day. And for all 30 days, we have to take this data and then we have to average it out. Okay, so it must be averaged it out for 30 days, right? So how to do that? So we have to take this data, okay, from this random process. We have to take this data at 1 p.m. and this data has to be taken for all 30 days. I equals to 1 to 30 because zeta I represents you the day 1, day 2, and up to day 30. So it will be giving you the data for all 30 days. And after that, we have to add all this temperature and then we have to divide it by the number of days. Okay, so this number of days must be 30 and this will be giving you this particular data over the 30 days, right? And now if I see, I can ask you this second question also. What is the average temperature between 11 a.m. to 3 p.m. on a day 3? Okay, so I'm asking about on day 3, what is the average temperature between 11 a.m. to 3 p.m.? Okay, so this is another question, right? So if I'm interested, what is the temperature, average temperature between 11 a.m. to 3 p.m. on day 3? I'm only interested about this particular sample function. I'm not interested about all the sample functions, right? So normally here, when I'm interested only onto this particular sample function to calculate this, what we have to do is we have to take the data at 11 a.m., then 12 p.m., 1 p.m., 2 p.m., and up to 3 p.m. And then I have to add all these temperature values, and then I have to divide it by 5 because we are having total 5 such samples. So if we do that, we will be able to calculate what is the average temperature during this time, 11 a.m. to 3 p.m. on day 3. So here, if you see the way I have asked the question, if you see in the first case, okay, while calculating this average, if you see, I have considered all the sample functions in this particular ensemble. Okay, I have considered all the sample functions. So normally this average is called as ensemble average. Okay, so here it is wrongly written. Okay, so please make this correction. This first one is actually representing you the ensemble average that you remember. Okay, this is your ensemble average, right? Because we have calculated this average based on the ensemble, okay, complete ensemble, because this ensemble is having total 30 number of sample function, and therefore I can call this as an ensemble average, right? Similarly, if you see this one, okay, because I'm considering only one sample function and I am considering only that particular day data, okay, at the different instant of time, normally this is actually referred to as the time average. Okay, so this is actually called as the time average. Please make this correction. Okay, this is your time average and this is your ensemble average, right? So similarly, whenever we calculate mean or autocorrelation function, okay, normally in the case of random process, okay, we are actually interested in the ensemble average. Okay, so here if you see this data, this particular expression, okay, this expression, whenever we are having the probability density function, in that case, the averages that we are calculating is actually known as the ensemble average. So this will represent you ensemble average. This is not your time average, you remember. Okay, so the time average, when we calculate, we have to just uh, do the integration of your time function only. Okay, and here you can see that it is not the time function. Okay, we are not writing this second sample function. We are writing in terms of your probability density function, and therefore when we do this calculation, this mean actually giving you your ensemble average value. Okay, so this is your ensemble mean, right? So similarly, we can also have the autocorrelation function. Okay, so here you can see how to calculate the autocorrelation function. So here we have to correlate a signal. Okay, suppose autocorrelation means we have to correlate a particular sample function, the amplitude of a particular sample function at two different instant of time. Okay, so suppose if we talk about this particular sample function, right? So normally, because here you can see, because in the case of autocorrelation function, what we have to do in the case of a random process is we have to multiply these two signals, okay, xt1 multiplied with the xt1, and then we have to average it out, right? So here again, this autocorrelation that we are performing over here, it is again a ensemble average. So how to calculate this? So let us suppose if this is your random process xt, then at xt equals to t1, if we have total number of sample functions equals to 4, 1, 2, 3, 4, in that case, at this point, whatever be the amplitudes of this, all random signals that we are going to get, it will be represented by the random variable x1. Similarly, at t equals to t2, the another outcomes of this all random functions at time t equals to t2 will be represented by another random variable x2. Okay, so here we have to take this random variables, right? And then what we have to do is we have to multiply all this data. Okay, we have to multiply, then we have to multiply this two data, then again we have to multiply this two data, then again we have to multiply this two data, and then we have to average it out over this particular sample function. complete sample function. So this way we are actually calculating this autocorrelation function. So this autocorrelation function will be represented by this particular expression. So here we have to average it out. We have to calculate the mean. First we have to calculate the product of the two. Then we have to go for the averaging out this product over its ensemble, right? And therefore this will represent you the ensemble autocorrelation function, right? So this is again your ensemble average. Try to understand. Okay, so this is also corresponding to this particular integration, right? This ensemble average can also be calculated by calculating by using this particular joint PDF. We can calculate this particular autocorrelation function. So Rx T1 comma T2 can be calculated if we have this second order statistics, if we have the joint probability, joint PDF in between x1 and x2, then if we follow this particular expression, we will be able to calculate this autocorrelation function. So normally this autocorrelation function can also be calculated, okay, because this expression can also be written in this form, okay, because we are talking about two different instant of time. Okay, so normally if we do this calculation, for example, if I taken here T1, then I can take this T2 at this point. Okay, I can also take this T2 at this point or somewhere else. Okay, we can take this T2 anywhere else in this graph. Okay, so we are actually correlating the amplitude of this random signal at two different instant of time. Okay, and it is a very important tool in the case of random process. Okay, it will be a very important tool. It is actually measuring the rapidity of your signal, right? So how much is the randomness or rapidity in the signal that can be measured by having this particular autocorrelation function, right? So here what I can do is instead of taking a certain value of T1 and T2, I can have this T and then I can have this variable tau. Okay, so T plus tau. So this tau can range from this particular value 0 to up to its maximum value. Okay, maximum possible value, right? So here this tau can be a negative value or it can be a positive value. Okay, and normally it is called as autocorrelation lag. Okay, or it is also known as the searching parameter. So because this tau can be a variable, so this tau can be 0, it can be less than 0, it can be greater than 0. Okay, so at a particular instant of time, this expression can be rewritten as this way. Okay, so here you can observe we have actually plotted this autocorrelation function for various values of tau for here two different random processes. So one random process is over here xt and another random process is denoted by yt. So here you can see in this case we are having 4 sample functions. Similarly here again we have this 4 sample functions, right? So when we calculate this autocorrelation function by using this particular equation, okay, for various values of tau, okay, so here you can, one thing that you can notice here the rapidity of the signal in xt is less as compared to a signal yt. Okay, this particular random process is a very rapidly varying random process, but as compared to xt, right? And here this xt is actually a slowly varying random process, right? So if you see its corresponding and this autocorrelation function graph. Okay, so here is the autocorrelation function graph, and as I said that this tau can be 0, it can be a certain positive value greater than 0, it can be a negative value. Okay, so normally the autocorrelation function will be a symmetrical graph around tau equals to 0. It will be a symmetrical curve, right? So here you can see whenever this signal is having less rapidity, then this autocorrelation graph is having more spread. Okay, it is having more spread as compared to the signal which is having very rapidity in nature. So whenever you will find that the autocorrelation function is having very narrow curve, okay, if it is very narrow curve, it means that the signal is actually rapidly varying signal. Okay, and normally this rapidity shows that there is less sample to sample correlations. Okay, so it means that the randomness of the signal is much more in this case rather than this case. So in this case, if we see there is a correlation between sample to sample, and there will be no much variation of the amplitude of your signal when we move from one point to another point. But in this case, if you see, there is a much more randomness. Okay, there is a much more variation in the signal over the time. So the correlation between one sample to the next sample is very much less, right? And whenever this correlation is weak, in that cases, this autocorrelation function graph will become narrower. Otherwise, it will be a very widespread. So this widespread graph denotes you that the signal is having less rapidity. Okay, so this is actually giving you the measurement about the spectral component. Okay, it will be giving you the idea of the rapidity of the signal, because we can have the random process, but which random process is fluctuating much more in the time with over the time, that will be reflected by this particular tool, autocorrelation function. So now we stop here today. Okay, so we discuss some more about this random process in my next video lecture. So thank you for watching this video. If you have any query, let me know with your comments. Thank you.